Good afternoon, everyone. This is Mr. Steele. I'm here with I think it's the final video solution set from the first half of Calculus AB. And it's going to be an involved one. This is a pretty long assignment because the lecture and lesson covers multiple days. It's almost a week of instruction just to kind of give you time to play with these things and get comfortable with stuff. So just know it's going to be pretty involved, but as always, I'll be linking the pieces on the actual problem set itself so that we can get right to the ones you want. In this video solution set, we're going to be working through the problems from, I believe it's the 23rd problem set of the term. This one's focused on related rates problems. It starts by just kind of building up the idea and the concept, gets into some fairly straightforward geometric problems, it gets to some of those more advanced questions involving things like area, angles of elevation, and where all sorts of different things are changing, and then eventually it gets to the cones and shadows and some of those similar triangle situations. Without further ado, rather than just talking about it here, why don't we jump into our first problem and we'll take a look at what's on top. Okay, the first question we're going to look at is question number 1. I wanted to make sure I covered a little bit of every type, so I'm erring on the side of doing more than less here. Just, that's the reason why there's going to be so many of these in here. So in question number 1, you are told first that y equals x squared minus 3x, and then second that dx dt equals negative 2. So in other words, they're telling us the rate of change of x with respect to time. So although they're calling this dx dt, we're going to call this ourselves x prime. Or you could even think of it as x prime of t itself, so that way we'll be ready should we need to use the chain rule. And it says that is the rate of change of x with respect to t when specifically x equals 3. Our job is then to compute dy dt. So in looking here, let's outline the process. This is a good enough example to illustrate what the process itself looks like. So there is our relationship, y equals x squared minus 3x. What we want to do is we want to take into account the fact that both x and y in this problem are changing with respect to time. So what we do is when we start, we are going to differentiate this, and it is implicitly, but we're differentiating with respect to a third variable t, which in this particular case likely stands for time. So what happens is when you differentiate with respect to time, neither the x nor the y actually features a t in them. They're different variables, which means that each one gets treated according to the chain rule, just like we did in our initial implicit differentiation work. Let me show you as an example here. If you take the derivative with respect to t of, let's say, y cubed. This isn't part of the problem, but let's take a look at what that would look like. Well then, because we have a y and we're differentiating with respect to t, we're going to do this implicitly. We'll have 3y squared, since that's what y cubed changes, or that's the rate of change of the slope formula for it. Then we multiply by the derivative, which is technically dy dt. It's the rate of change of y with respect to t. This is the chain rule that we're doing here. We would often write this as 3y squared times y prime. Now, on the other hand, if we had ddt of, let's say, x to the 4th, then we're used to just going 4x cubed done and finishing it, washing our hands of the entire situation. But in this case, because we're differentiating with respect to t and not x, that means we do the exact same thing we did just right up here. Our derivative of x to the 4th is, of course, 4x cubed, but then we need to take into account that x is changing with respect to time as well. So we'd multiply that times dx dt, or more practically speaking, as we've done so many times, multiply by x prime. So basically everything gets the implicit coverage, everything needs the chain rule, because our variable isn't there. And a good way to think about this is in reality what we're doing is we're pretending each of those is in fact a function of time. So for instance, the derivative with respect to t of x of t to the 4th, and if we take the derivative of that, it's going to be 4x of t cubed times x prime of t by the chain rule. And you can see the only thing that's different is we just didn't include the of t part of the notation. So it's just kind of implied, it's in there. And when you're differentiating implicitly, an implied thing seems fairly appropriate. So with that in your background, let's actually do the problem. It's not actually a very difficult one here, especially with an explicitly defined relation right off the bat. So as we go to differentiate with respect to t on each term, we're going to get the derivative with respect to t of y is just going to be dy dt, which I'm going to call y prime. Derivative of x squared is going to be 2x, but then we're doing it with respect to time, so it's going to be times x prime. And then the derivative of 3x is 3 times the derivative of x with respect to t. So you could see it that way. You might also see it written this way. I simply, as I'm sure that I would say in class or said in class if I was there, this is just another notation for it. Both notations are formally equal, and of course this would be ambiguous because it doesn't say what our variable we're differentiating with respect to is, but as long as we did this on our first step, this second line is totally fine. So there's no downside to it. So in here, at this point, then it's just a matter of like translating and plugging in the right information. So looking up here, looking at what we have, they tell us that dx dt is equal to -2. So I'll do it this way. dx dt equals -2. So that's going to be -2. Other pieces up here, they tell us that x equals 3. So this will be 2 times 3. So we're translating the x down into there. Minus 3 times x prime. Oh, there was one of those as well. I should have made that switch early on. So times -2. So that came right down to there. And then for y prime, we don't know what y prime is, but that's okay, because we're trying to figure out what dy dt is, which is just another way of saying y prime. So in our equation here, you can clearly see that we just have y prime by itself equal to this expression on the right. And simplifying all this, we get -12 plus 6 is -6. So y prime, which we're going to call dy dt, is equal to -6 at this time. And so we have our rate of change of y. And again, the reason that our answer comes out with a rate of change of y, right, with respect to t, is simply because we knew what x was changing with respect to. We knew how x and y were related to one another. So our result is just a particular rate that comes out of that relation. So when we perform related rates problems, we're really relating some information together, and then we're differentiating to get their rates. And that relationship will create two related rates, or maybe even more related rates, which allows us to solve this. Now, before we wrap this question up and move forward on to our next question, let me make one small caveat or point here. In this situation, once we differentiated, we didn't actually have any y's left in the problem, but it's certainly possible that we could have started with, say, y squared here, and be left with y on the actual equation. So let me point out that if you have to figure out what y is, you can take that x equals 3 and use the fact that y equals x squared minus 3x. If you want to figure out what the value of y would be, you could just plug in 3. And in this case, you'd get 0. So that means that the point x equals 3 corresponds to the y value 0, and so you'd be able to find it as well. We just didn't need it in this problem, so I didn't investigate it in this problem. So there is a really overdone first example, but I think that really lays some great foundation for the rest of the problem set. Okay, next, we're going to take a look at 3A. 3A is the story of the ant, which actually in computer animated movies was a big thing, I think, in the late 90s. Had Bugs Life and Ants both come out in the same year, racing to get an insect movie. Neither one was great. Go figure. So in 3A, we are told an ant is moving along the curve y equals 4 root x. So they're talking about a particular curve. Right here it's describing the ant's path, I guess. But we can sketch what this function looks like. It's a radical, it's been stretched a little bit, maybe even make it a little bit taller. But there is the curve itself. This is y equals 4 root x. So that's a good start. And it says that the ant is moving along the curve such that dx dt is greater than 0. So in other words, they're saying x prime is positive. Well, translating that into our picture, if x prime is positive, that means the rate of change of x is positive, which means it's moving in a positive direction. So our ant, which, you know what, let's go grab a picture of an ant. Let's cooperate. Yes. He's facing the wrong direction. Let's fix that. Okay. So our ant, thank you Pixar for providing our ant. It says that x prime is positive. That means that our ant is moving along the curve in this direction because its x velocity is positive. So horizontally, it's moving in a positive direction. In fact, I realized I could just do this. Let's see where it's moving by adding arrows. Okay. So it's moving in that direction. So the question for us to answer then next is dy dt positive or negative? So the question is, as the ant follows that curve moving towards the right, what is its y-coordinate doing? Well, and if you imagine here, it's actually not hard to figure out. As the ant moves right, its y-coordinate gets higher and higher. And in other words, that means dy dt is greater than 0. So right off the bat, we can figure out that that's true, or in other words, dy dt is positive That's another way to say it. Both of those are fully acceptable. Nothing wrong with it. But the question might be, okay, well, we saw the picture, but how would we know otherwise? Is it even possible to support it in another way? And the answer is yes, of course it is. So for here, what I did to answer that why was I kind of made a visual picture of what the situation looked like. We could also do this as a pure related rates question. So I'm going to differentiate that relationship with respect to time t. And I know it's with respect to time t because each of these has dt in the denominator. Taking the derivative, we'll get dy dt equals 4 over 2 root x times dx dt. So looking at the piece of information we have here, looking at our stuff, the right side is going to simplify to 2 over square root of x times x prime, and that's all equal to y prime. Well, looking at our values here, 2 over root x is clearly greater than 0. Has to be. The square root of a number is positive without any sort of negative sign on the outside. 2 is positive, so their ratio has to be positive. And x prime, we are told, because x prime and dx dt are the same, we are told that this is positive. What that tells us is that we've got a positive times a positive, which is clearly greater than 0. So the implication is that y prime is greater than 0, or better yet, dy dt is greater than 0. So we were able to support it using just a pure related rates kind of construct as well. What? Cannot save it? Unexpected error? Oh, error. Boy, we don't want to save my work, do we? Let's go somewhere else. An unexpected error is being saved. Okay, guess we're not going to be able to save that file, but with any event, we've got 3a down. We've seen two different ways, one very visual and graphical, the other one a little bit more involved, but using the related rates work that we've just worked through. Okay, that next brings us to question number 4. Question 4 tells us, or asks us, to first consider a linear function y equals mx plus b. So let's give it all its consideration we could possibly ever want. Okay, we did it. It says if x changes at a constant rate, so dx dt is changing at a constant rate, so we'll just call dx dt some constant k. Does y change at a constant rate also? So we're interested in about what happens when we let dx dt equal a constant, and whether or not that implies that dy dt is a constant. So we'd be looking to see if we get a single value out of here as well. Do they change at the same rate? Let's check. So to do this, we want to consider what's happening as x and y both change with respect to time. So we're going to take the derivative with respect to time of this entire equation. We'll of course get y prime equals m times x prime. And then b is just a constant without any variable whatsoever, so its derivative remains 0. So that means y prime is equal to m times x prime, or better yet, dy dt equals m times dx dt. So far so good. There we go, we have a relationship. Now things that we know is m being the slope is constant. And second, we also know that dx dt is a constant because, and bear with me here, they told us it was. So what that tells me is that we have a constant times a constant, and that product of two constants is equal to the rate of change of y. So that tells me, since constant times constant is constant, it implies that dy dt is constant also. So that gives us our first answer. We were able to just show that both pieces of the derivative were a constant, so dy dt is a constant. The second question they ask is, do they change, they being x and y, change at the same rate? So our question is, does dy dt equal dx dt? And the answer, of course, is no. No, they are different, and the reason is that we have that constant value of the slope multiplied times dx dt to produce dy dt. The slope actually scales this rate of change, and so it means that they are both constant, but they are different. They are proportional to one another, but different. But at the same time, there is one possibility for which those two things would be the same. Do you recognize what it would be? That one possibility, that they would have be the exact same rate, would be the same if m equals 1. So if m equals 1, then we'd have dy dt equals 1 times dx dt, in which case we would say that the two are changing at the same rate. So with that said, there's number 4. It's a little weird, it's a little bit more conceptual and abstract, but still something you can get through using computation and just by thinking about the meaning of the different parts of this linear equation. Okay, question number 6. 6 moves us into the world of geometry, like trying to solve some geometric problems, excuse me, and work through when things are changing and how we can relate those together. So in question number 6, the first thing we're told is that the area of the square is changing at a rate of 3 square meters per hour, when its side length is 12 meters. So area of a square is changing, and we have a side length. At what rate is the perimeter of the square changing? So we're going to be involving perimeter, area, all sorts of stuff. So let's just kind of quickly make an inventory of what we have, in addition to the fact that we're talking about a square. So play for that. So first of all, we're talking about the area of a square, and the area of a square is just s squared. You take one side times the other. It's length times width, but with length and width the same. Second, we're asked about perimeter, and for a square, each of those side lengths is exactly the same, and there are 4 of them. So the perimeter will be 4s. So we're going to have to do something involving that s, obviously, but we also have a and p. Sorry, trying to make that look a little bit more like an s. Next, we know that the specific time we're interested in, the snapshot moment, is when s equals 12 meters. And then the question we're asked is to find p prime. So basically, there's our inventory of stuff that we know and that we have. Now it's a matter of just... oh, there's still one more piece. It says the area of the square is changing at a rate of 3 square meters per hour. So the area is changing. That would be dA dt. And that is 3 meters squared per hour. Sorry, almost missed that piece of information. It's an important one. So with that said, we now have a complete inventory of what's going on in this problem and what our situation looks like. Now it's a matter of starting to do the actual relating and the production of the rates. So the first thing we're told is that the area of the square is changing at a rate of 3 square meters per hour. So we know that the area of a square is equal to s squared. We want to talk about how fast or at what rate it's changing. So to begin attacking this, we're going to take the derivative with respect to t of that equation. When we do, we're going to get dA dt, or what we like to call for simplicity a prime, is equal to, well, the derivative of anything to the second is 2 times that stuff, times the derivative of that stuff. So we have a prime equals 2s times s prime. There is the rate of change of the area equals 2 times the side length times the rate of change of the side length. So from here, what else do we know? Well, reading our information that we have, I see over in our inventory that we know dA dt, or a prime. That's all this is just a prime. And it says it's changing at a rate, so it doesn't say increasing or decreasing. So this is going to be 3. On the other side, we have 2 and then s. And look at that. They told us s is 12. So 2 times 12 times s prime. And we're trying to figure out what s prime is, I guess, because that's the only thing that's left. So without further ado, let's just find it. Again, maybe we're doing something wrong, but I think we're in good shape. This tells us that 3 equals 24 s prime. And doing a quick division on both sides, we're going to find out that s prime is equal to 1/8. And if you're looking for units, it would be meters per hour, but not essential just yet, so hang around for just a bit. So there is s prime. Now in an easier problem, you'd just be done. You'd go, cool, that was what I was looking for. I wanted the side length rate of change. Done. But in this particular situation, we want to go a little bit further, because we are specifically asked in this problem to determine the rate of change of the perimeter. So at what rate is the perimeter of the square changing? So let's take a look at that relationship. P equals 4s. Well, if we want to know how the perimeter is changing, that means we want p prime. We need a p prime. So I'm going to differentiate this perimeter equation with respect to t. Pretty common technique. When I do, sorry, I should have been an imply symbol up there. When I do, I get dp dt equals 4 times ds dt. So in looking at this equation, you might think, well, shoot, there's 2 variables in there. But really, we know that s prime is equal to 1/8. We found that in the previous problem. we can connect those two pieces because these rates are indeed connected, or I should have said are indeed related, but whatever. We can plug in that 1/8, and we'll get that P prime equals 4 times 1/8, and that tells us that dP dt is equal to 1/2. So there is our rate, or our perimeter's rate of change as a magnitude. What it's missing here is the units. Like, we don't have the units yet. A couple different ways to get there. There's lots of different ways to work your way through. We could have put in the meters per hour squared, or meters per hour here, and then figured out that it's meters per hour. Or you could look at the way units of perimeter are measured. Perimeter is just summing up a bunch of lengths, and lengths are measured in meters. So if we're looking for a rate of change of meters, we point out that P is measured in meters. And second, we point out that T is measured in hours. There is the answer to our question. So again, you'll notice you've seen all the greatest hits of things to do in a related rates problem here. You've written out some geometric formulas that were pretty simple. You've drawn a diagram and labeled it as best you could. You've differentiated some stuff. You've plugged in some stuff. And then you've identified the units correctly. And in this case, we even did it multiple times. So not too shabby, I would say. Okay, next that brings us to question 8. Question 8 is a personal favorite from here. Really enjoy this question. And our situation's changed. We're no longer looking at a square. We're looking at, I believe, a triangle. So the problem says, both the height and base length of a triangle are changing. So we have a triangle with a height and a base. The height of the triangle is growing at something while the base length is shrinking. Okay, well, excuse me. Okay, let's just get through the worst part here. Let's sketch out our triangle. There's the triangle in question. They're telling us some information about its height, so I'm going to give a variable h for the height. And then they're talking about its base, so I'm going to call that base b. So again, this is just me kind of getting my mind around what's actually going on. The next part says at the instant when the height is 11, so we can start filling in some information here. The height is 11 millimeters. The base length is 4 millimeters. At what rate is the area of the triangle changing, and is the triangle becoming bigger or smaller at this time? Give a reason. So what I'm doing is I'm trying to again create like a short little inventory to make sure I have everything that I'll need here. So I've got the height and base, but what else we have here is we're talking about the rate of change of the area of the triangle, and that tells me that I need to have a relationship for the area of the triangle, and presumably it would be one that featured both b and h. Well, think back for a second. What is the area of a triangle? Well, it's going to be 1/2 the base times the height. So there is the relationship that represents our area. Our job is to figure out the rate at which that is changing. So that's going to be our final move here, to plug in stuff after we differentiate. Excuse me. Okay, so in digging in here, let's start with that equation. Again, we don't have much else to go on here, except for those specific values. So I'm going to write this out as my area formula, and then I want to figure out how fast it's changing, so I'm going to differentiate it all with respect to time. So when I do that, looking on the left side, the derivative of a with respect to t is what we're just going to call a prime. On the right side, though, we got to be careful here. This is 1/2 b times h, which means it's really a product. So for simplicity, I'm going to write this as 1/2 b times h, because that way I can write out using the product rule. I can't remember if I said that a second ago, but whether I did or didn't, let me point out again we need the product rule because we have two different functions being multiplied and we're trying to take their derivative. So in this case, we're going to have d dt of 1/2 b times h plus 1/2 b times d dt of h. So there is our derivative all there, ready to go. Could clean up a little bit. In fact, let's do that. So a prime is going to be, well, the derivative with respect to t of 1/2 b is going to be 1/2 times b prime. And of course, we still have an h there. And on the second one, we do have 1/2 b. And then we have the derivative with respect to t of h. That's going to, of course, be 1 times h prime. So now that we have both of those two components, or both of the two terms differentiated and ready to go, using the product rule, of course, we can start to substitute the pieces of information that we have, and then see if we can't figure out the rest in just a second. So as far as pieces go, we know what the area is equal to, but that's not actually going to help us too much now. We've already done that work. We do have that h is 11, so basically that guy is going to be 11. We also have that b is 4, so again that's 4. And then looking into our problem, is there anything else up there that we could draw out? I feel like we're short a piece of information. Aha! Aha! The height of the triangle is growing at 2 millimeters per second. So the height's rate of change is positive 2 millimeters per second. And I knew that it was positive because it says the height is growing. And when you grow taller. At least that's the implication here. So h prime is positive 2. So that means we're going to have a positive 2 on our hands right there. And third, or fourth, depending on how you look at things, our other piece of information says that the base length is shrinking at 6 millimeters per second. So we called our base 6. So you might be tempted to just write 6 millimeters per second, but technically that's incorrect for our rate. Can you see why? Hopefully what's catching your attention is the word right here. It says the base of the height of the triangle, or the base length of the triangle is shrinking at 6 millimeters per second. That means this won't be positive 6, but negative 6, to build in the fact that the values of b are getting smaller and smaller. So weird to think, the triangle is getting smaller vertically, but stretching out further to the sides on its own. So a couple little pieces here. That was b prime we just found, so we can go ahead and substitute that in as well. As far as the other ingredients that we have, everything else that's on that right side is already a constant. So we have 1/2 times this plus 1/2 times that. So for the sake of simplicity, let's go through and actually simplify this. So the first one is going to be 1/2 of negative 66, which is negative 33. The second one is going to be plus 4, which gives us an overall rate of change of negative 29. So first, I'd rather have units here. So we're talking about area units. So area is measured in units squared. Looking at our particular problem, if we look at the rate of change of the area, or this one, we'll notice every single term has a b and something, or sorry, a b prime and an h, or an h and a b prime. So that brings us all the units that we need. But in any event, area implies units squared, so that's probably how I think through this problem, if I'm being honest. So we're measuring millimeters, so I'm going to venture that this is millimeters per second, or millimeters squared per second. Sorry, I wrote it right, I didn't say it correctly. So voila, there's our work for 8. So interesting stuff about number 8. It's the first one to use the product rule, so it's a pretty big move. It was also the first one that when we did the product rule, we ended up with 2 separate different derivatives on the same side, and a third one overall to work through. So that takes us through question number 8. I think it's a really rich question, especially with that product rule in there. It's a good check to make sure you've remembered all your differentiation rules. Okay, this brings us to question number 10. So 10 is based on a true story from a couple summers ago, or a couple years ago. So we're talking about Miss Nakamura's daughter, Jalen, who's I think going into 3rd grade this year. So it says, while playing on Mr. Steele's computer after school, Jalen creates a circle on Microsoft Word. While making the shape, she then begins to move the mouse wildly and gleefully around the screen, as little kids tend to, causing its radius to change at a rate given by r prime of t equals 8 sine of t squared over 17 plus the square root of t, measured in pixels per second for the first 30 seconds. If the radius of the circle was 847 at t equals 13 seconds, at what rate was Jalen's circle area changing at t equals 13? Okay, so for this particular problem, we can actually illustrate what's happening here. Since again, this is based on a true story. Let's see here. Let's draw in a circle. The circle, let's make the outside really, really thick. Let's make the inside less so. Okay, so in this situation, the radius is changing. She's doing like this. Whee! So notice the radius of the circle is sometimes getting bigger, sometimes it's getting smaller, sometimes it's staying the same, although we can't really tell that. Our goal is to figure out what the actual rate of change is at a particular instant, given the rate of change of that radius, which in our problem was given to us as r prime. So in looking here, let's start with a quick little inventory. Let's see if we can get out everything that we do know in this situation, and then see what we can bring together. So let's see, what are we doing? She begins with the was. So Jalen creates a circle, and then later it mentions a circle's area changing. That screams to me that we need the area of a circle, and you should know that the area of a circle is pi r squared. Pi times the radius squared. Notice that units would be radiuses, or the units of radius squared per minute. So as a heads up, if you're looking for units here, or per second, sorry. If you're looking for units here, looks like our units would be in pixels squared per second. So there are the units. No, that's not the units for A. The units for A would just be pixels squared. I apologize. So we have A. We have other information, but most importantly, we're interested in knowing some stuff about what's happening when A changes. So let's change it ourselves. Let's take the derivative with respect to t of A equals pi r squared. So of course the left side becomes A prime. On the right, we're going to have pi times. Well, the derivative of anything squared is 2 times that anything, except then we multiply times r prime. So there is our relation of those rates, or that is the related rates setup of the problem. Now it's a matter of us getting the rest of the information out of here. So looking at some ingredients that I see they give us this complicated expression for r prime of t. What is it? 8 sine of t squared over 17 plus the square root of t. So we've got a very complex modeled function to show how that radius was changing as Jalen moved the mouse up and down and changed the size of the circle. It also says that the radius was 842 pixels at t equals 13. So in a sense, what that's telling me is that r of 13 is equal to 842. So we can call this r, because that's our specific snapshot moment that we're interested in. So looking down here, what else do we got? Okay, let's just see. We got a prime equals pi times 2 r times r prime. And then in looking at all of these ingredients, you might think that we don't have enough to solve this equation because of the fact that we don't know a prime and we don't have a number for r prime either. Darn, we've put everything into our problem so far, haven't we? You're right, we have not. There's still a piece of information coming out of that problem statement that we have not used. Specifically, we know that r prime is equal to that complicated expression. And the reason that's relevant, I'll use it in just a moment. Just get one more line here. So just simplifying a little bit, I'm going to have 1684 pi r prime equals a prime. So just to make sure that we're all here, let's take a look at this last little piece. If this is r prime of t, then that's just another way of writing r prime, which means this expression, a prime equals 1684 pi times r prime, is going to be multiplied times, with parentheses, 8 sine of t squared over 17 plus the square root of t. So this is the expression we need to calculate. We need our calculator to help us with, unless you're just really good at evaluating signs of quadratics of some kind, quadratic binomials. But we can definitely make this happen. So in fact, let's go grab the graphing calculator here. Could have done it on Desmos or something, or Wolfram Alpha, but we'll stick with the calculator. Okay, so what we wanted to calculate here, we want to do 1684 pi. We want to multiply that by the quantity 8 sine of, what do we got here? Oh, it's 13 seconds. Oh, look, I missed one thing. Look at that. Look how easy that is. It said we were at 842 pixels at 13 seconds. We used the 842 and the 13 here already. What we didn't do, though, is we didn't plug it into the function itself for r prime. We want specifically r prime of 13. So we're going to take that t squared and we're going to put 13 in. We're going to take that t and put 13 in as well. That way all we have to do is literally just plug this into the calculator. So 1684 pi times quantity 8 sine of 13 squared over 17. I think that's equal to about 10, isn't it? 169 over 17 is about 10, a little under 10. The other thing that we have is we have to add to that the square root of 13. There it is. And without further ado, ooh boy, not a fun answer. Negative 1822. Negative 1822, 349. So there is our area's rate of change with respect to pixels per second. Since it's an area, we need those length units squared, and then the time units stay consistent. There is our work. There is our stuff. We've done a good job through question number 10. Okay, the next question for us to attack is question number 11. We'll attack both parts A and B, just because each one doesn't give you the formula for stuff involving cubes. Figured it'd be a good time to talk about it. So in question 11, we're first told that the edges of a cube are growing at a rate of 5 centimeters per second at the instant when the sides are 20 centimeters each. So as far as cubes go, it's a good idea to draw one right off the bat, just to kind of remind you and give you some context. So, learned how to do that in 3rd grade, I remember. I think I remember being taught perspective lines, in fact, there. So if you're a big fan of perspective, there we go. So there's our cube. It's telling us that the sides are each 20 centimeters. So I'm going to call the sides, you know what, I'm not going to call them S. I'm going to call them X for simplicity. So every side of this cube is a length X. And we're told at the beginning that every X is 20 centimeters. And if you'll recall, one of my recommendations is I put variable lengths, like descriptive variables on the outside, and then the specific snapshot times on the inside. So there it is in place. So from here, the next thing it says the edges are growing at 5 centimeters per second. That'd be like saying dx dt, codename x prime, is equal to 5 centimeters per second. So there's where we're beginning. The question we're asked about, though, is to find the rate at which the volume of the cube is changing. So that's what we want to know, is the volume of the cube. So it's worth asking yourself really fast, what is the volume of a cube? Might be something that panics you. Well, think about it this way. In order to create a cube, what we do, you can imagine one way to construct a cube is we take a square, set it down on the bottom, and then we stack on top of it a whole number of thin slices of paper as well. It's almost like a stack of Post-it notes. There we go. One that will eventually become a square. So we stack them on top of each other, so we have the area on the base times however tall it becomes. More importantly here, if you take the volume of a cube in this way, the area of the base, here I'll do it this way, we'll go base area times the height. And then if we look at our specific situations, our base area would be x squared. Our height is exactly the same as well, it's x. That means the volume of a cube is just equal to x cubed. Easy to remember, cube, cubed. Good stuff. So that means that we now have that the volume is equal to x cubed. And then we're interested at the rate at which it's changing. So we can take the derivative with respect to t of both sides of this equation. This should go fast now. We'll get dv dt on the left. On the right, we'll get 3x squared. But remember, x is changing also with respect to time. The sides are literally changing. So we need a dx dt, or x prime. And then over here, we already said x prime is 5 centimeters per second. And they're growing, so it is in fact a positive 5 centimeters per second. So we can plop in the 5 centimeters per second. We can also point out that the sides are 20 centimeters each. So this will be 3 times 20 squared times 5. And as far as stuff here, we have 3 times 400 times 5. That's going to be, let's see, 3 times 2,000, I want to say. Yeah. Which is 6,000. And then as far as units, we're looking for the units of volume. So you could use volume units and point out that here it'd be centimeters cubed, and we're measuring time in seconds, so per second. So there is our volume rate of change. If the units give you trouble though, you could also go up to here and look at it that way. We'd have 3 times centimeters squared times centimeters per second. And if we multiply out those units, we'll get centimeters cubed per second. So either way we do it, we get the correct units. And we've just completed question 11A. That next brings us to question 11B. In 11B, we're still talking about the same cube. The edges are still growing at 5 centimeters per second, and the sides are still 20 centimeters each. But this time we want to know the rate at which the surface area of the cube is changing at this instant. So to get here, we need to know what is the surface area for a cube. So a good question to answer this would be to once again look at our drawing of a cube. And I'm going to go once more and grab this. Grab that X as well. Okay, so there's our cube. So the surface area is basically what is the sum of all the areas on the outside. So thinking about this, a cube consists of 6 squares. So there are literally 6 squares. And if you don't believe me, imagine a traditional die or a dice when you go to roll it. Dice have 6 sides on each one. It's a 6-sided dice. It's a cubically shaped dice. So there are 6 squares. Each one has the same area because the lengths and widths are all the same side lengths or edge length. Each one is x units. So that's 6 squares of area x squared. So that means that our total surface area, I'm just going to call it SA, is going to be equal to 6x squared. We add up each of those 6 squares that have area x squared. From there, the rest of the problem proceeds pretty traditionally. Differentiating with respect to time, we're going to get surface area prime, I'm just going to write it that way, is equal to, it looks like 12x times x prime. As far as our lengths and pieces, we know that x is 20 centimeters. We know x prime is 5. This is going to give us the surface area rate of change we want. This is going to be 60 times 20 is going to be equal to 1200. And as far as units go, since we are instructed to include units, we mentioned earlier, this is going to be measured in centimeters times centimeters per second, which of course gets us centimeters squared per second. And that should make sense that these are the units because area and surface area are measured in square units, and then we're measuring with respect to time, so per time unit. Okay, that next brings us to question number 12. Question number 12 fits into that kind of mold like the Jalen pixeling question. In question 12, we're told first, a large right cylindrical tank in a lab has a radius of 9 feet and a height of 40 feet. So I'm just going to go ahead and start by marking that on here and drawing a quick little diagram. So there's our stuff. It has a radius of 9 feet. So let's label that in there. So that's 9 feet. And then the height itself, the full height here, is 40 feet. So good to know. There it is. There's my can. Liquid is being pumped into the tank by a malfunctioning hose such that the height of liquid in the tank at any time is given by, let's see, where h prime is measured in feet per hour. So it says that the height of liquid in the tank, that's actually incorrectly stated. That should say the rate of change of the height. So basically we're saying how fast the height is changing inside there. So we're looking at how fast the height is changing. So basically you can imagine what we got is we're pouring water in. At one moment the height's down here. A few instances later it's here. Maybe after the same number of instances it's there. Then maybe it accelerates a little bit faster. So we're slowly filling up the liquid inside this tank. And we know how fast that height is rising thanks to that. So from there it says that the height of the liquid at time t is 13. So in other words, if h of 7 equals 13, we want to figure out at what rate is the volume of water changing. So we want to figure out what is v prime, also known as dv dt. So that's where we have to begin our investigation and our search. So looking up here, it looks like we're going to have to deal with the v prime. We're going to have to find the derivative of the volume. And looking over there, they gave us they gave us the equation V equals pi r squared h, which looking at, you might start to think, based on the presence of both an r and an h, that we're going to need the product rule for. Here's the thing though, we actually aren't going to need the product rule, and the reason is based on the shape of the cylinder. So we know that what's going to happen here is as water moves out of the hose into the tank, what's going to change is going to be the height of water inside the tank. Basically the height h is just going to keep rising. So h is going to be increasing, but notice that as we move that water up, the radius of that circle doesn't deviate from 9 at all. The reason is the outside dimensions stay constant. So in reality, what we have is that either r is constant, that would be one way to think of it, or you could think about it the same way as dr dt is equal to 0. Because based on a solid cylinder, the radius doesn't change. The base area doesn't change, only the height inside changes. So given that, you have two options here. There are two ways you could progress. The first way that you could progress, or let's go option 1. Your first option would be to use the product rule. So using the product rule, you'd have to do both of these derivatives. I'd probably go pi r squared and h as my two functions and do each one. And then when you go to evaluate and plug in stuff, I'd take into account that dr dt is 0, and I would end up zeroing out one of the two terms. The second option, which is the one that I hold on to, is I just go ahead and let r equal 9, because we know it's constant, and that's all that it really requires for us to actually work through this problem, is we just need to know what that actually ends up being. So what I mean is this. If v equals pi r squared h, it's the same thing as v equals pi times that constant r of 9 squared times h, which means our volume equation is actually 81 pi times h. So from here, we can take the derivative of this expression with respect to time. And again, let me remind you, this will be the same as if you do the product rule and then evaluate the dr dt as 0. So just know there's nothing different. Either way, it's better than the other necessarily. From there, we're going to get v prime, or dv dt, is equal to 81 pi times h prime. So looking in here, we were trying to figure out at what rate the volume of water is changing. That's what we're trying to answer, which means that we must know what h prime is equal to. And in fact, we do. They tell us that h prime of t is equal to this expression, e to the negative 0.1 t plus ln. That is messy. They give you a messy expression, but we can still use that. V prime is equal to 81 pi. Actually, let's do this, just for the sake of colorization. Let's toss this in there really fast. So V prime is equal to 81 pi times, and then we're going to put in h prime of t, which is e to the negative 0.1 t plus the ln of t squared plus 3t. So there is all of the stuff that we have to look at. So looking in there, there's our expression that we need to go through. And at first you might say, okay, well then what do I do? Because I still have t in there. But there's one last piece of information present for us. It says in the problem that we're interested in what the rate of change of the volume is at t equals 7. So what we need to do is we need to evaluate this at t equals 7 specifically. So in other words, go ahead and draw this up here for the sake of space. We want to calculate and find dv dt, or v prime, as 81 pi times e to the negative 0.1 times 7 plus the natural log of 7 squared plus 3 times 7. So we just need to calculate out what that value is equal to, and that'll give us the rate of change of the volume. And of course we can do that by plugging in on our graphing calculator. Like, I don't know if every other calculator has E and ln buttons, so maybe a scientific would be okay too. So 81 pi times, let's put it in parentheses to make sure we don't mess anything up, will be e to the negative 0.1 times 7. It'll be then plus the natural log of 7 squared plus 3 times 7. And pressing enter, we end up getting our volume's rate of change. So dv dt is 1207.476. So that's going to be our dv dt, or v prime. Either way you do it, I guess technically it's an approximation. And with that in place, the only thing left is to, of course, include units. So let's think about this in terms of the quantities we're measuring. I always prefer to do that myself. So we're measuring this as a volumes rate of change. Our time is measured everywhere in hours, so it'll be something per hour. And then for the volume itself, we're talking about feet everywhere. Everything's measured in feet, feet, feet. All those things are feet. So this will be for volume units, this will be feet cubed per hour. And there is our rate of change of the volume. So again, it's something to get used to as you're looking at some of these problems. I'd say these ones that have these really strange looking H primes or R primes of things end up feeling like they're some of the strangest problems, and they look like they're really, really difficult. But truthfully, all they're doing is giving you a recipe to plug in a derivative or to calculate a derivative at a particular point. You just treat it like anything else, substitute it in, and then evaluate using your calculator, because these are almost all calculator questions. Okay, and then for the last one that I'm going to do today, I'll finish up the rest of them tomorrow. Let's look at our first Pythagorean problem. So in our situation here, we have an 85-foot long ladder, which that's one heck of a ladder, is leaned up against the side of the building by Stooge Construction Company. Unfortunately, the base of the ladder begins to slide away from the building at a rate of 8 feet per minute. So let's just start with a quick little illustration of what it is that we're talking about here. So I'm going to draw a building. You can see it's just amazing craftsmanship there, isn't it, though? Just isn't it beautiful? So next we'll draw our little ladder. So our ladder is starting here. And then what they're saying is it starts to slide outward that way, which means that you'll have the ladder look like this later. And eventually, if we let it go far enough, it'll be basically horizontal later on. So obviously that's a little bit hard to read. So for the sake of visibility, let's do this. I'm just going to draw a ladder. So there's our ladder length, and we know, because ladders don't change length, if they do, that's scary, they're just going to start falling off. This is 85 feet all the time. The ladder's not going to change length, all likelihood. So there's our ladder. What else we got here? Base of the ladder sliding away at a rate of 8 feet per minute, so we're moving in this direction, 8 feet per minute. At the moment when the base of the ladder is 13 feet from the edge of the building, at what rate is the vertical height of the ladder changing? Include units. So they tell us right away that this length is going to be 13, but keep in mind that as the ladder falls out further, that length gets longer and longer. It's actually approaching the length of the ladder, which, if it eventually falls, will be literally 85. So since that's there, it's actually changing, and I'm going to call it X. And of course, since the ladder is falling down the building, or sliding outward, we can imagine that the ladder has to be falling downward as well. So I'm going to call this Y. And of course, we don't know what the actual amount is at that instant, but we can find that in just a second. And in fact, that's what we're asking here. We're asking what rate is the vertical height of the ladder changing with units. So let's go through and do a couple different things here. So let's look at some pieces, see if we can fill in some gaps, and then get ready to actually work through this problem. So, of course, I'm going to mark this a right triangle. Definitely is a right triangle. That's always a good thing. So we're talking right triangle. Next, as I look at the ingredients, I know this side length at the instant we snapshot. I know this ladder's length because it's always 85. What we're missing is the length of Y at that instant. But since this is a right triangle, we can use the Pythagorean theorem. In fact, that's going to be an essential component of this triangular situation. So we're going to use the Pythagorean theorem first to figure out what that third side is at the snapshot moment. So in looking here, we know that 13 squared plus whatever that y squared is going to be equal to, excuse me, has to be equal to 85 squared. So with that said, we want to figure out y. Y is going to be the square root of 85 squared minus 13 squared. And I don't happen to know that one off the top of my head. So 85 squared minus 13 squared. I hope it's a nice number. I can't tell. Let's square root it or take it to the 0.5 power. We get 84. So this is 84, and that means at that snapshot instant when we're 13 feet from the base of the building, we are actually 84 feet above the floor as well. So now we know the specifics of that situation. When we snapshot, we know all the relevant dimensions. Now second, we've got to think about the actual equation we're going to need to take into account here in order to relate these rates. And that equation is going to be the exact same one we were considering before, the Pythagorean theorem. because that's going to relate all three sides of this triangular situation to one another and allow us to differentiate them all together and really relate those rates. The difference is here we can't use 13 because 13 is changing. Anything that's changing has to be represented as a variable, because otherwise if you put in a constant, its derivative will be 0 and we'll miss some of that essential movement and motion built into this situation and scenario. So what I mean is, for the Pythagorean theorem, I'm going to use the equation x squared plus y squared, because of course those two things are changing. As the ladder goes down, the height falls, and as the ladder goes down, the horizontal distance gets bigger. And x squared plus y squared is going to be equal to the hypotenuse squared. But since our hypotenuse is that ladder, and the ladder's length is unchanging, it's just going to be equal to 85 squared. So that is the equation that we're going to be using and working through. So in fact, so that it stays, I'll leave it right there, and I'll move it down so that we can differentiate it. Because our next move, as with every related rate, is to start differentiating with respect to time, and start to look at how those rates are connected. So each of these is pretty simple. The derivative of x squared is 2x, but because x is changing, we multiply by dx dt. It'll be 2y, but y is changing, so we'll multiply by dy dt. And finally, 85 squared is just a number, and the derivative of a number with respect to any variable is just 0. So basically, this is the relation that's going to hold for us. And in fact, the 2's can divide away on both sides, and we'll just get that x prime plus y prime equals 0. So at this point, it's now just up to us to come up with all the variables and plug everything into the right spot. And a few of these are really easy to get. We already stated earlier that 13 is going to be our x value at the snapshot instant, and we were told that x prime is going to be 8 feet per minute. And since it's moving away from the building and further out, you can tell that this length is getting larger, so I'm going to leave this as a positive 8 feet per minute. And again, that's because it's moving this way. You can imagine that if our system was on a coordinate plane, moving in that direction would be equivalent to moving towards the positive infinity value. So from there, we'll next look at y. We know that y itself is going to be 84. We calculated that out up here using the Pythagorean theorem first. And we don't know what y prime is, but we're trying to figure out the rate of change of the vertical height, so that's a good thing. We've got the right variable missing in our equation, and of course the sum of those two things adds up to 0. So pulling this all together, we can start to solve this equation for what we need. 8 times 13 is going to be 24 plus 80, which is, I believe, 104. And if we subtract we'll just go 104 plus 84y prime equals 0. Solving this equation a little bit. Sorry, it's going backward. Actually, I'll move it this way. We're almost there. So from there, if that equation is true, then negative 104 equals 84y prime. And that means y prime, which we would probably more formally call dy dt, is going to be equal to negative 104 divided by 84. And of course, we can simplify that a little bit. That's going to be negative 52 over 42, negative 26 over 21. So there's our stuff. And of course, we need units. So what rate is the vertical height of the ladder changing? So let's see. It should be measured in feet, and it's y over t, so feet per minute. So now our answer here of negative 6 over 21, or negative 26 over 21 is a good answer. Seems pretty accurate. But more than anything else, I want to point out the importance of that negative sign. As our ladder slides down the wall, its y value is getting smaller and smaller. It starts high, and the ladder starts slipping, gravity starts pulling it downward, and it starts getting smaller and smaller. That means that our answer should in fact be negative to this question because the vertical height is decreasing. So we want the y prime to be less than 0 so that it actually meets that requirement of decreasing. Since we got negative 26 over 21, we got our negative value, and it looks like everything is matched up really nicely. So with that said, that was kind of a basic Pythagorean problem. Hopefully, though, it did a good job of clarifying some pieces for you, and you feel pretty comfortable with this.